Welcome to Thermodynamics lecture series. In the present video, we will discuss the first law of thermodynamics. Before going to the first law of thermodynamics, we will discuss the concept of internal energy. Internal energy is the heat energy stored inside a gas. So let's see what happens when heat is supplied to the gas. When heat is supplied to the gas, temperature of the gas may increase or gas may expand, which means increase the volume, and this is causes for the do the external work, or both temperature and volume may increase together. If the temperature of the gas increases during the heating, then its internal energy also increases. Next we will discuss the Joule's law of internal energy. Joule's law of internal energy states that internal energy of a perfect gas is a function of temperature only. In the other words, internal energy of a gas is dependent only on the temperature change and it is not affected by the changes in pressure and volume. In this regard, we cannot find the exact value of internal energy in a substance, but in engineering, we only need to know how much the internal energy changes. In general, internal energy changes are expressed in the terms of delta U. So next we have to discuss for the law of conservation of energy. In the early 19th century, scientists are discovered that energy cannot be created or destroyed. So this idea is called as the law of conservation of energy. So based on the law of conservation of energy, energy can only change from one to another. So energy is always constant. It only changes its form. Then first law of thermodynamics is based on this law of conservation of energy principle, and this is mainly deals with the heat energy and mechanical energy. So next we have to discuss about the first law of thermodynamics. So let's see the first law of thermodynamics for a closed system undergoing a cycle. For a closed system undergoing a cycle, heat energy and work energy can produce similar effects in a system, and both heat and work are simply different forms of energy, and this energy is always conserved. So energy can enter a system as a heat and leave as work, or it can be enter as a work and leaves as the heat. So according to the law of conservation of energy, the total work done by the system is equal to the net heat supplied to it. So therefore, first law of thermodynamics for a cycle can be stated as when a system completes a thermodynamic cycle, the total heat supplied to the system is equal to the total work done by the system on its surroundings. So mathematically we have to say the first law of thermodynamics. Summation of net heat supplied to the system equal to the summation of total work done by the system on its surroundings. This first law of thermodynamics cannot be proven mathematically, but it has been repeatedly verified through the experiments. So let's see the small experiment. So to discuss the first law of thermodynamics, consider a closed system containing a fixed mass of water placed inside an adiabatic vessel. This vessel is equipped with a thermometer to measure the temperature and a paddle wheel for the stirring, as illustrated in the figure. So here I have to observe the figure. So in the figure, insulated container is containing a fixed mass of water, And also this container is equipped with a thermometer which is used for the measure the temperature change of the water, and also equipped with the paddle wheel for the stirring of the water. Assume that a certain amount of work W122 is done on the system using the paddle wheel, and this work can be determined by measuring the drop of weight which has to be rotates the paddle wheel through a pulley mechanism. So here we are applying a certain amount of the work, let's consider W122, on the system by using of this paddle wheel, and this amount of the work we have to determine by, so just we have to drop off the weight. So due to this drop of the weight, this paddle wheel has to be the rotate through the pulley mechanism. Let us consider initially the system is at a temperature T1 which is equal to the surrounding atmosphere temperature. After the work is done on the system, temperature is increases to the T2. So let's consider initially temperature of the water is the T1, but after the work done through the rotating of this paddle, then water temperature has to be increases T2. Moreover, throughout this process, pressure remains the constant at the 1 atmosphere. The process from state 1 to state 2 is represented in figure using generalized thermodynamic coordinates of the x and y. So I have to observe the another figure. So here we are representing the process state 1 to state 2 by using the thermodynamic coordinates of the x and y. Now if the insulation is removed, the system exchanges the heat with the surroundings until it returns to its initial temperature T1, reaching thermal equilibrium with the atmosphere. So after the work done on the system, so then temperature is increases from the T1 to T2. Then if the insulation is removed, then system again exchanges the heat with the surroundings. Then temperature again reaches from final temperature T2 to its initial temperature T1, reaching the thermal equilibrium with the atmosphere. During this process, the amount of the heat is transferred, that is the Q2 to 1 from the system can be measured. So here process 1 to 2 is the work done on the system, that is the W122. So here work is enter into the system. Then after the insulation is removed, then heat is transferred from the state 2 to 1. So here work done 1 to 2 is work done on the system, and the Q2 to 1 is the heat transferred from the system. So then the system completes a thermodynamic cycle. In this cycle, a certain amount of the work W122 is done on the system, followed by the rejection of the heat Q221 from the system. So it has been observed that the work input, that is W122, is directly proportional to the heat transfer, that is the Q221. So mathematically, summation of the work done in the cycle is directly proportional to the summation of the heat transfer in this cycle. So summation of W cycle is directly proportional to the summation of the Q cycle, which is equal to the summation of W cycle equal to the J into summation of Q cycle. Here J is the proportionality constant. It is known as the Joule's equivalent or the mechanical equivalent of the heat. So this is also expressed in the form of, so integration of dW equal to the J into integration of dQ. So therefore the constant of proportionality J is the equal to unity, that is J equal to the 1 Newton meter per the joule. So in the above simple case, there are only two forms of the energy transfer. One is the work, another one is the heat. However, if the cycle includes the multiple process, additional energy interactions may be needed to be considered. So even if the cycle includes the several heat and work interactions, the same conclusion holds that net work done is proportional to the net heat transfer. So finally we have to state the first law of thermodynamics. When a system completes a thermodynamic cycle, the total heat supplied to the system is equal to the total work done by the system on its surroundings, and also stated as heat and work are mutually convertible, but since energy can neither be created nor destroyed, then total energy is associated with an energy conversion remains the constant. So this is the introduction of the first law of thermodynamics.